She sells seashells by the seashore. I don't really know where I was going with that, but we're talking about seashells, and to be specific, about how seashells inspire a new way of creating recycled plastics that can actually make them useful for our daily lives instead of just being a fad. So if that's got you excited, then let's hit the seashells. All right, before we talk recycling and material science, let's talk about today's sponsor, Mouser Electronics. And dear friends, if you've been listening to the pod for a minute, you know that we're big fans of Mouser here at The Next Bite. And the reason is pretty simple. We made this podcast to talk about interesting tech in a way that's really easy to relate for everyone. And Mouser, by being one of the world's biggest electronic suppliers, has a lot of cool connections to folks in academia and in the industry. And they write about the cutting edge of technology in these bite-sized pieces of content. One of them that we're going to be linking in today's show notes. But the reason I found it interesting is because how relatable it is to today's content, which is about how do we recycle e-waste properly. The article that Mouser has essentially goes over, old phones and computers are piling up. Shout out to all of you that decide to ditch your iPhones after 1 year when they, at least have a couple years left in there. And we need to figure out how to extract the necessary critical components of it, the precious earth metals and even the plastics if possible. But that's really challenging because there's so many nuances in how they're assembled and so on and so forth. So the article talks about how robotics and AI are being leveraged to process these PCBs and these electronics as well as we possibly can. I don't know. I thought it was interesting. They go into the sensors required to detect the components, how to extract it, rip it apart, and the damage or actually the benefit it has for our global economy and the environment. Just a fun all-around article, and it's really easy to read. I think I read through the whole thing in 3 minutes, so definitely check it out.
Check it out in our show notes. Also, it's interesting to note, there's a startup called Moog AI that is a partner with ABB. They make robotic arms, multi-degree of freedom access robotic arms. And they're based in Sterling, Virginia. So like less than 5 minutes from my house.
You're kidding.
And they're partners with HP, ABB, Dell, and the Climate Pledge Fund and Stanley Black & Decker. And their whole thing is about using robotic arms to do disassembly of old e-waste. And then they also actually do some circular manufacturing in place too. So they won't just disassemble the previous products. They'll also assemble them into new ones, which is pretty sweet. And they're just down the street from us. So if anyone knows anyone at Moog, it'd be cool to check it out because I would love to go there and see what they're working with. But just a testament to Mouser being on the ball. There's this new tech startup that just recently received $5 million grant from the Department of Energy, and they're literally 5 minutes from our house. And Mouser's writing about this, this new segment of using robots and AI for e-waste.
Apparently, their CEO lives in Reston.
Yeah, which is
we
where
might be
Forbode
neighbors.
lives. Yeah.
All right. Well, I'm going to send a connection to them. See if we can do an episode.
That'd be super.
That would be awesome.
Yeah.
All right. Well, look at that. Adventures midway through the episode, or
I know,
start of the episode. That's what you sign up for with The Next Bite. Adventure time.
Exactly.
That said, let's go to Georgia Tech. And no, I didn't pick this article because it's Georgia Tech.
Yeah, if anyone doesn't know, Forbode's a student at Georgia Tech, so take any biases he has about Georgia Tech being awesome with a grain of salt. But if I tell you Georgia Tech's awesome, you can believe me.
Yeah, I might say this is the best article we've done this year, but that's not because I'm biased, despite what Daniel says.
Yeah.
Regardless, let's talk about plastics. So I think, Daniel, you and I have never directly discussed this topic, but we've talked about it in tangent to other discussions about material science.
For sure.
But we love material science, and the topic of recycling is very contested, let's say. Some do it religiously, some don't do it at all. And then in the industry as a whole, the use of recycled materials, at least in the facade of it all, is very encouraged. But in practice, it's not necessarily the case. There's an interesting statistic that was shared in the article that says something like less than 10% of the 350 million tons of plastics produced each year is effectively recycled. And the main question, I guess, the average listener might have is, well, why? It seems like you can, drink the water from your water bottle, put it in the recycling bin, and then it goes to some facility where they can melt it down and make something else. Why isn't that encouraged more? Why aren't there more people who want recycled products? And it all just comes down to mechanical performance, right? When you go from a virgin plastic where the polymer chains are nice and neat and tight, and then you shred it up, melt it down, those mechanical properties that you originally had are now being degraded. And when you think about applications like automotive, aerospace, anything that even has some level of mechanical property requirement, they're not going to be so happy about degraded mechanical performance.
For
But
sure.
it's not just
like,
that.
It's actually kind of crazy. We recently visited actually Padnos. They're one of the largest recyclers in the world. Visited their recycling facility in Grand Rapids, Michigan, where they do most of the plastic recycling for lots of plastic waste from all the automotive manufacturers in the Detroit metropolitan area. And they've got tons and tons and tons of plastic come in there, and they've got awesome processes to make sure that everything's clean and uniform. And like you're saying, you shred it down, you melt it, you make a new material from it, and the cost of this plastic is generally cheaper or competitive with virgin plastics. But the concern, like you're mentioning, is the mechanical performance. And when you're an engineer trying to specify using some sort of plastic for a certain application, you're going to want to make sure that it's strong enough to be able to handle what you're doing. Or really, what that means is when a plastic is stronger, you can use less of it, which means it costs less. And that's what the salesperson was telling us from the recycling team is like, hey, actually, the cost of oil per barrel has gone down a little bit. So now, for the same application to use virgin plastics, it actually might be cheaper than using recycling because of the mechanical performance issue.
Right.
So if you can find a way to improve the mechanical performance of the way that we use recycled plastics, you can decrease the effective cost of using recycled plastics, which makes the incentives right to where people are willing to use recycled plastics. And then it reduces or increases the amount of recycled plastic that's palatable for people to use. And that's like really the disconnect right now. You mentioned 350 or 400 million tons of plastic are wasted every year, but most of that ends up in landfills or the ocean. It's not because we don't know how to recycle it. It's because there's no incentive for anyone to want to buy recycled plastic. There's no usage for it, or not enough usage for it that we actually end up using all of that. Most of it ends up getting put into landfills or the ocean, which is obviously an outcome that we want to avoid.
Absolutely. On top of that, with virgin plastic, there's a margin of error that is predictable with the properties, right? So like plus or minus, let's say 1% for tensile strength or whatever. You don't necessarily get that with the recycled products. There was a quote that said something along the lines of every piece of recycled plastic has memories of its past, and it means like whatever processes were done to it slowly degraded it in its own unique way almost. And that means, like you're saying, as an engineer that's trying to even use recycled plastic, not only do you need more of it, but within that, from part to part, there might be deltas that are too significant for production. So that's another parameter that you have to keep in mind. And all that to say, there's this problem of, can we make better use of recycled plastic, or are we just stuck in this vicious cycle of having to rely on virgin? And these Georgia Tech folks, they had a pretty good answer. They said, why don't we just look at nature? Because unlike us, nature doesn't strive for perfection. It kind of organizes and makes do with what's already there. And to explain that a little bit better, they're trying to use seashells as a biological example of something that takes rough, hard minerals that are not organized well, different shapes, different sizes, different properties, and then it binds it together with a soft gel to create a structure that's actually really strong and performs quite reliably. And they were trying to think of, is it possible for us to be inspired by that same methodology of creating materials to make better use of the recycled plastics that exist today, to bring a certain level of strength and reliability back to recycled plastic products?
And I love the usage of biomimicry here because seashells are very, very strong in aggregate. But if you look at the ingredients in seashells, the minerals are actually pretty weak compared to lots of other minerals that exist in nature. The proteins that connect all these minerals are actually quite soft and stretchy. So how do we build these strong seashells out of weak minerals and soft proteins? It feels very similar to trying to solve the problem, which is like, hey, we've got these polymer chains that used to be long, but now they're chopped shorter. So they're not as long, they're not as strong, but we still want to make end use plastics out of it. I love that they looked at this analogy in biology, and the answer they found is like it literally looks like a brick wall or a brick and mortar structure where there's hard blocks of minerals held together by softer protein glue. They want to mimic that with recycled plastics. And spoiler alert, they found improved mechanical performance when they mimicked what we see in biology, which is like this brick and mortar type structure.
And obviously, articles are great. We're doing our best to explain what's going on. Highly recommend for those of you that are visual learners like me to go on the actual site and look at this short video they have of the new material developed by the Georgia Tech team, where they have these recycled high density polyethylene recycled sheets that are laid down like bricks, as Daniel's saying, with this adhesive in between them acting as the mortar. And they start to apply this force to stretch it out. And you can see kind of the concentrations of the force as the material is being ripped apart. And you see, I don't know, the material in action, and things start to click, at least again for me, because I'm a visual learner. But like, it's absolutely amazing what they've been able to accomplish by, you know, essentially creating a composite material and proving that recycled materials don't just have to be this unpredictable thing. The most impressive of the numbers of their experiment is that they were able to reduce the variability and the maximum elongation. So, you know, you have a piece of plastic, you're pulling it to failure by over 68% in comparison to the original methods of producing recycled plastic materials.
And also the variability in the stiffness of the material as well.
Right.
That dropped to 93%. So
right.
tensile elongation is like the measure of mechanical strength for a lot of stuff, but also stiffness matters a lot in the applications where you were saying, oh, I need to thicken this material. I need to use more material to make sure that it's stiff enough to stand up to the mechanical stresses. Kind of going back to the problem at the beginning where we're saying on a per mass basis, recycled plastics may be cheaper, but in an application usage cost, it actually may be higher because you need more material to make it stiff enough. They're able to reduce that variability in stiffness by about 93%. And what's interesting is the data point that this is all converging on is that it's about comparable in strength with new plastic as well. So it's much more consistent than recycled plastic, and it's also just about as strong as new plastic, meaning that we're starting to enter this realm where it's a competitive drop-in replacement for virgin plastic.
Agreed. But, you know, I think the environmentalists might also be happy to hear that the estimate the researchers are giving is that it's possible to cut the manufacturing cost of virgin packaging materials by nearly 50% and offer savings of, again, their estimates, hundreds of millions by providing this like alternative that's actually reliable as a solution into the plastics world. Personally, I think that's a little ambitious, but Love the energy. I love where their head is at. And I like that they have data to back up, again, that we haven't hit a wall with recycled plastics. You just have to get a little bit more creative and maybe just look into nature for inspiration on how to do things a little bit different.
Yeah, for sure. And one of the most interesting things for me, um, just thinking about unlocking new potential applications of technology where we hadn't seen it before, this also enables them to do chemistry agnostic recycling, is what they said. So right now there's some plastics that are recyclable and there's some plastics that aren't recyclable. And a lot of the plastics that aren't recyclable, again, it doesn't mean that we don't know how to use it. It's just the mechanical properties of that plastic after we're done recycling it is nowhere near the original use, and there's no marketable use for the new end material. So they say no, it's not recyclable because we can't use it. It's not to say that we don't know how to process it, but in this case, they were able to actually test industrial stretch film, which is like the plastic wrap that they put around pallets and packages to protect them. Normally that can't be reused. And as you can imagine, if we're using it to wrap every single package and every single pallet in the industrial world, there's a lot of usage of this industrial stretch film. Well, with this method and their tests in the laboratory, they were able to get recycled industrial stretch film that matched the stiffness of brand new film. So in this case, they are not only potentially unlocking recyclability or applications of recycled plastics where we already know how to do recycling, they're also potentially unlocking new types of plastics to be recycled that are already matching the same mechanical performance as brand new plastics. And obviously, there's several factors at play here, but if it costs about the same or less, it's better for the environment and it performs about the same or better, why wouldn't you use this new material?
Personally, I'm very excited about that because what can and cannot be recycled is a heated topic in my household, where I'm the one that's constantly looking at the back of the packaging for the right logo, and then everyone else is just chucking everything plastic into the recycling bin. So, yeah, we're very happy to hear that.
Me too, man. You want to wrap us
All
up?
right, wrap it up. Yeah, let's do it. Folks, plastic is a problem. We know that we have these insane landfills that we've just been piling up, and recycled plastic was supposed to be the savior. You don't have to worry about dumping it. We can just make it into something else. But lo and behold, that hasn't panned out like we thought. The reality is that recycled materials just aren't as strong as they need to be. But the researchers at Georgia Tech think that they have a good solution for it, inspired by nature, seashells to be specific. They think they found a way to stack up these tiny shredded up pieces of plastic with a mortar like adhesive to create a material that's almost as strong as the original one, which would enable engineers to use these new recycled materials with much more comfort. So, this little tiny inspiration from nature might make a huge impact on the way that we produce and recycle plastics in the near future. Mic drop. It's actually on a stand, so no dropping.
Not going to drop it.
Nope, impossible. All right, folks, thanks for listening. That's the pod.